Okay, so picking up here where we left off on the last video, plus a little more, we ended up the last video, we had developed this relationship between wavelength and frequency, and we were relating those through the speed of light. So if we know one of those quantities, wavelength, we can calculate frequency. If we know frequency, we could calculate wavelength. Unfortunately, the last video, I had to cut it off because I had a battery issue with my calculator. So I already went ahead and did part of the problem here. So I've got my solar-powered calculator. So let me just explain what's going on here. So in the problem here, we've got a certain type of light. So the yellow light given off by a sodium vapor lamp. These are reasonably common street lamp bulbs. The wavelength of this light is 589 nanometers, and we want to figure out what is the frequency of this radiation or this particular light. So I used the version of the formula here that isolates frequency on one side. That would be the speed of light divided by the wavelength. And if you plug in the speed of light there, it's in meters per second. And hopefully you would recognize, well, I need to cancel that meters out in order to have the units for frequency left, which will just be per second or hertz. So the wavelength has to be in meters in order for those cancellations to happen. So in this case, we need to take our wavelength in nanometers, convert that to meters to have the right set of units. Now, 1 meter is a billion nanometers, or 1 times 10 to the 9th nanometers. That is a factor that I'll give you. That's not one of the ones I said you should memorize back when we talked about chapter 1. But basically, I calculated that wavelength in meters. Then I plugged it in up here, right? And that's when my calculator betrayed me. Well, not my calculator, but its batteries died, and I don't have that particular battery at the moment. So I switched over to the solar calculator once I found it. Plug these in, right, 10 to the 8th and 10 to the minus 7th. That's going to give us a big number. And we've got a pretty big number already, but now we're dividing by a really small number. So it's probably a good idea to try to evaluate your exponents like that, because this is a problem that does pop up. People have kind of weird habits of plugging in their exponents that don't always do the math they think they're doing. So this should get should be a bigger exponent, right? We're taking an already big number and dividing by a really small number. What I got when I punched this in was 5.09 times 10 to the 14th power, right? And the units are per second, right? You can rewrite that as hertz. I'm not a big fan of hertz because canceling out the seconds is often important. So that would be the frequency of this particular light. Okay. Second example. Here, we've got a radio station broadcasting at a frequency of 1,150 kilohertz. Now, kilo prefix, we kind of know what that means, but we'll have to factor that in as we do the problem. And in this case, we want to solve for the wavelength. So we're given the frequency, we want the wavelength. So we return to our original discussion of the equation. Right? There's a version here that we can use to solve for wavelength. The wavelength would be the speed of light over the frequency. Now, similar to the problem we just did, right? If we plug in the speed of light, the time unit in there is per second. So that matches with hertz. Hertz is per second, right? A kilohertz doesn't quite cancel out with a hertz. So we do have to do a little unit manipulation before we really can plug in here and solve. So speed of light is the same, 3 times 10 to the 8th meters per second, right? But I want to get this to hertz or just per seconds before I plug it in. So 1,150 kilohertz, right? And in this case, 1,000 hertz would equal 1 kilohertz. So multiplying that by 1,000, which is just moving the decimal 3 places, that would be 1,150,000 hertz, right? Which is also per second, right? Which is how I like to think about canceling up here. If I plug that in up here, per second, right now I've got seconds on the bottom of the top of the fraction and on the bottom of the fraction, and so those cancel out. And this will just leave us with meters. So this will give us the wavelength in meters. So 3 times 10 to the 8th divided by 1150000. And that gives me, to three significant figures, 261 meters, right? And we talked radio waves are on that side of the spectrum where they have really long wavelengths. So, right, 261 meters, that is a pretty big wavelength for our radio wave light. Okay, now those I think would qualify as fairly straightforward problems, just two variables, frequency and wavelength, right, relating them to the constant. The other thing that we'll want to talk about in terms of light is its energy. So if we want to evaluate energy of light, we need to factor in energy units somewhere, which is joules. Now it turns out there's another constant, Planck's constant, which is abbreviated with just a lowercase h, is 6.626 times 10 to the minus 34th joule seconds. So this is joules multiplied by seconds. Now if you just think about those units, joules times seconds, maybe you can imagine if I multiply by the frequency, that will leave me with just joules, which is energy units, right? And that basically is one of the formulas we want to think about. Energy of light, capital E. Now, when we talk about energy of light, we're kind of shifting a little bit to talk about photons of light or individual particles as opposed to waves. Now, light has this duality where in some circumstances it acts like a wave and some it acts like a particle that maybe we don't completely understand. But this equation refers to each individual photon, what energy it has. Energy is equal to Planck's constant times the frequency, right? And again, unit-wise, this would be energy in joules. Planck's constant is joules times seconds, right? And our frequency is 1/second, so the seconds would cancel out there in the equation. So if we know the frequency of the light, right, we plug in Planck's constant, we can figure out the energy of each photon of that light. Now, we know from above that frequency is equal to the speed of light over the wavelength. So combining E equals h nu with nu is equal to c over lambda gives us another version of this equation that would relate to wavelength. So E is going to be equal to hc over lambda. So if we want to compare the wavelength of light to its energy, we just need to multiply Planck's constant times the speed of light, divide by the wavelength in meters, and we'll be left with joules here again. So in this case, joules for energy, joules times seconds for Planck's constant, meters per second for speed of light, right? There goes seconds. Divide that by the wavelength in meters, there goes meters, and we would just have joules left over, okay? So energy and frequency are directly proportional, right? If the energy goes up, that means the frequency is going to go up. But energy and wavelength are inversely proportional. Longer wavelength would be lower energy because we're dividing by a larger number here. Smaller wavelength would be larger energy because we'd be dividing by a smaller number, right? So we want to use both of these equations as well to now kind of relate energy to these other properties of light. Okay. Now, we got a couple of problems here, but I don't know that we can get through one of these and still keep the video in a reasonable length. So let's stop right there. We'll build on those two formulas in the next video.